The objective of this video is to continue developing the regulator design approach using Bode plots and outline the effect of loop gain on closed-loop regulator tracking performance. So on the top here, I've sketched the block diagram of our closed-loop regulator, and on the bottom, I've brought over the frequency response, or the Bode plot frequency response, of the small signal model for the power converter that we were talking about in our previous video. And we'll be building up upon this as we go through the lecture. First, back to the block diagram of our closed-loop regulator, we're going to define some new terminology. And the new term is called the kernel of the loop gain. So if you'll recall, we defined our loop gain as being T of S, which was, if you start here where the error is and multiply your transfer functions all the way through and end up here, this whole path is T of S, or your loop gain. The kernel of the loop gain is the transfer function Tk of S, which is equal to the loop gain divided by your regulator. So it's equal to all the blocks in this block diagram, the multiplication of all the transfer functions of all the blocks, except for the regulator. So in this block diagram, we start on the left side with our error term, and moving to the right, we have our regulator, which is not going to appear in the kernel of our loop gain. And then we have a PWM block, which is used to convert our control voltage into D tilde, our duty ratio, our small signal duty ratio. And moving to the right of that, we have the transfer function for our converter, which we derived last time for a specific case. And then on the bottom here, we have our negative feedback factor, or our sensor gain. So the idea is that the kernel of the loop gain is equal to everything in this path here, but does not include the regulator, so that we can write T of S is equal to our regulator transfer function times the kernel of the loop gain. And this is for convenience. This lets us talk about the circuit simpler. So we can, in other words, if we go back to our Bode plot down below here, we can say that last time we plotted the kernel of the loop gain, and then last time we also considered the design of a regulator, and when we combine the regulator transfer function with Tk of S, or in other words, we combine the regulator transfer function with the kernel of our loop gain, we end up getting the total loop gain transfer function. And now let's summarize the rules for regulator design that we introduced a couple of videos ago. And those rules were that we want to cross the 0 dB point when the decibel plot of our magnitude is at a slope of negative 20 decibels per decade. And we want to have a GCF that is less than our PCF. And remember, GCF stands for gain crossover frequency. That's when our magnitude plot crosses the 0 dB point. And PIF stands for phase inversion frequency. That is when our phase is at negative 180 degrees. So, so both of these quantities pertain to our total loop gain. And right now, as drawn, this loop gain, the kernel of the loop gain, does not actually have a gain crossover frequency because it's never larger than 0 decibels. It doesn't cross over the 0 dB point because it's never larger than 0 decibels. And it doesn't have a phase inversion frequency because we never hit negative 180 degrees. Our third and final rule was that we want to have our loop gain at frequencies much, much smaller than our gain crossover frequency. The magnitude of this should be much, much greater than 1. So the first two rules here relate to stability of our closed loop system, and they also relate to our transient response, whether we have overshoot or undershoot or ringing on our output waveform in response to a disturbance. The third rule pertains to our steady state response. This relates to how much error we have in our system in the steady state conditions. And we're going to talk about these rules throughout this lecture, building up progressively through an example, but I want to start by talking about this notion of stability, this notion of the gain crossover frequency needing to be less than the phase inversion frequency. And one of the ways that we had talked about stability before was by writing out the expression for our closed loop transfer function as the famous black equation. And we noted that if the phase angle of T of S is 180 degrees, negative 180 degrees, when its magnitude is 1, this expression explodes. It has a divide by 0 in the denominator. That's because when the magnitude of T is 1 and its angle is at negative 180 degrees, it evaluates to negative 1. And so you have, on the top, you'd have a negative 1 over 1 minus 1, which would be 1 over 0. And we know that is infinity, negative 1 over 0. And we've also talked about stability in terms of the roots of the closed loop transfer function and how you can determine that from a Nyquist plot and a simple test of the Bode plot, which is what we're talking about now. But at the moment, I want to give a little bit more physical meaning to what happens when we have a phase inversion. So at the phase inversion frequency, the argument of T of S is equal to negative 180 degrees, when omega is equal to 2 pi times the phase inversion frequency. So this magic number of a magnitude of 1 with an angle of negative 180. So when we have an angle of negative 180 and we take our path around here, that means that at this point right here, if we had an error, the value at this point right here is equal to beta times T of S times our error. If our error is at a frequency that T of S is equal to negative 180 degrees, this becomes a negative number, which feeds into our error calculator and becomes a positive number. So it becomes actually a positive feedback situation. So you go from epsilon here, you come around your loop, and you add in back a positive epsilon. So suddenly now you evaluate this and you've got 2 epsilon. And then you take this around the loop again, and you come back again, and now you have 4 epsilon. So it keeps adding and growing unboundedly. So you can see that that's a problem. That's going to cause stability issues. And we know that all physical systems have a loop gain that goes to 0 as the frequency goes to infinity. It's like if I try to talk really fast. If I have a lot of thoughts in my mind and I'm trying to talk really, really fast, pretty soon my mouth cannot keep up to the speed that I am talking at, and the output of my mouth goes to 0, right? My muscles physically cannot move fast enough to generate the sound, and so the volume goes to 0. And the same is true for our power electronic circuits. At a certain point, we can keep giving higher and higher frequency references. We can keep commanding higher and higher frequency duty ratios at this point. But at a certain point, our converter is just not able to possibly move its output voltage in response to the frequency of the duty ratio. The transients are just too fast. The inductors are too stiff. The capacitors are too large. And so we know that that's true. And so the kind of one of the obscurities about this analysis is that, you know, we're only worried about the phase inversion frequency coinciding with the gain crossover frequency. So that means we're only worried about the phase inversion happening when the gain of our loop transfer function is unity. And that's because if we have a phase inversion at a much higher frequency than our gain crossover frequency, if we have a phase inversion somewhere way out here, we have the magnitude of our loop gain is so low that it does not matter that it gets added back in up here. So if you start out with 1 volt over here, you come around here, and it gets multiplied by 1/10, negative 20 decibels, it is positive feedback, but it only adds in 1/10. It only adds in 0.1 volts. Or if you're out here at negative 40 decibels and you go around this loop, it only adds in 0.01 volts. So at these points, it does not matter that we have this small positive feedback path. And at low frequencies, when we want T of S to be very, very large, this right here, it looks like 1 in parallel with TS. And so at low frequencies, when TS is really, really large, this just ends up looking like 1. It doesn't matter what your phase is doing particularly. Okay, so that's building up a little bit more our notions of our physical intuition for what stability means and how we interpret it on our Bode plot. Next, we're going to continue developing our physical insight, our physical intuition for these rules, but now we're going to consider an example of a regulator design. Suppose that we choose a function equal to 10, which is 20 decibels. And remember that our operative transformations tell us that our magnitude plot for our loop gain is going to be, since it's going to be GR1 times the kernel of t, in decibels that's going to be GR1 plus TK plus the kernel of our loop gain in decibels. So we can add this on to our plot up here. We'll sketch a single red line at 20 decibels, and then we'll sketch the combined transfer function of the actual loop gain of our system. So we're going to add these two, which just shifts this blue curve up by 10 decibels. So if we draw that, my drawing is a little bit skewed, but the point is that this green line and this blue line should be parallel as they decay down. All we've done is shifting the blue line up by 20 decibels. And right here, we now have a gain crossover frequency. I want you now to, on the phase plot, on this bottom plot, so we're calling this T1 because it's the loop gain for regulator option 1. So sketch the phase of the loop gain. And I want you to tell me what the phase inversion frequency is and what the phase margin is. So press pause, sketch it on this graph down here, and press play when you're ready to resume. So our operative transformation tells us that when you multiply two transfer functions, you add their phase angle. And the phase angle for GR1 is just 0 degrees. So when you add these two phase angles to get the phase of your loop gain, you end up actually simply retracing the kernel, the phase angle of the kernel of TK, the kernel of the loop gain, which does not show up very well on here. And so what is the phase inversion frequency? It does not exist. The phase never crosses the negative 180 degree point, or never hits the negative 180 degree point. What is the phase margin? Well, the phase margin does exist. That is the angle between negative 180 degrees and the argument of your loop gain. That is your phase margin. So that is 90 degrees. So this is a plausible regulator. If we look at our rules, we see that it has a gain crossover frequency. When it crosses over, our slope of this line is negative 20 decibels per decade. And that's true because the slope of this line was negative 20 decibels per decade, and we just shifted up by 20 decibels. So we passed the first test, we passed this test. Our gain crossover frequency is less than our phase inversion frequency because our phase inversion frequency doesn't exist, or it's infinity. And there's a bit of question for this last test. Certainly our loop gain is greater than 1 or greater than 0 decibels at low frequencies, but whether or not it's much greater than 1 is a little bit open for discussion here. So let's try to develop some theory to analyze whether or not the gain is sufficient at the low frequency regime. So again, we can talk about this through our closed loop frequency response transfer function. Where we'll specifically just talk about this portion of it, which is again 1 in parallel with T of S. And we want this portion to be equal to 1. If that is equal to 1, that means that this down here is equal to 1, which means that we exactly track our input voltage without any error. However, we know that can't physically happen, but that is what we're trying to make happen. That's our objective. And so if we unpack this a little bit, we can see that how close that is to 1 depends on the value of T of S. If we have 1 in parallel with 1,000, if T of S at a specific frequency evaluates to a gain of 1,000, then we can see that this truly is very close to 1. If we have 1 in parallel with 10, well, I mean, we can plug that into the function. 1 over 1 plus 10 is equal to, I apologize, 10 over 1 plus 10 is equal to 10 over 11, which, you know, is fairly close to 1. It depends on what your design spec is, but it's reasonable to believe that that could satisfy a design spec that you have. And again, remember, this is your design spec in terms of your error tracking capability, your maximum ripple on your output. So maybe that's good enough, maybe not. You'll have to look at your design spec. And remember, this 10 corresponds to our 20 decibels, which is what our loop gain is right now at low frequencies. Right here at low frequencies, we have 20 decibels. If you have 1 in parallel with 2, well, now you're living pretty close to the edge. You evaluate to 2/3. It's still closer to 1 than it is to 0, but yeah, certainly you have very noticeable error. And if you have 1 in parallel with 1, well, now you have 1 over 1 plus 1, which is equal to 1/2. And so you can see that you certainly have sizable error at this point. And this corresponds to a situation when T of S is at the gain crossover frequency. When T of S is equal to 1, or 0 decibels, you have this situation taking place right here. So that means that at frequencies corresponding to this point right here, you will have noticeable error. And so we can make kind of a general statement about this. We can say that at frequencies below this point, where we have a rather large gain, presumably, assuming that we follow this rule, our feedback is effective. But at frequencies above this point, where our loop gain keeps getting less and less and less, where we keep going down this path here, our feedback is not effective. And we can take this one step further. We can notice that we're talking about, again, 1 in parallel with T of S, and we know how to do that operation on the Bode plot. We talked about the parallel operation in our operative transformation video, and the parallel operation is if you have 1 in parallel with TS, that means that your decibel plot is going to be equal to the minimum of 1 and T of S. So I know I just did this in red, but let's put in our decibel plot in purple. So this is going to be the Bode plot of our closed loop regulator, scaled by some value of beta afterwards, but that's a rather arbitrary distinction. There's no frequency component of that, it just is a constant scaling factor. Let's take a look at what this looks like. We've got our loop gain here, and 1 is just a plot along 0 decibels. So if we're following the minimum of this, we're going to follow a path that looks like this. Here our loop gain starts to become less than 1, so then we follow it down. And you see that we have the purple transfer function. We call this point right here, the point where the feedback stops being effective, as the bandwidth of our regulator. So at frequencies below the regulator's bandwidth, we can say that feedback is effective. At frequencies above the bandwidth, the frequency is clearly not effective. And we motivated all of that by this discussion of having 1 in parallel with a transfer function, by evaluating, what that actually looks like for different gains of our loop gain, different values of our loop gain. The bandwidth of our regulator, new term, or in some places you'll see this called the FB frequency or omega B, is the same as our gain crossover frequency of our loop gain. And the gain crossover frequency in some places will be called f sub c, or omega c equal 2 pi fc. Okay, so we've now introduced this concept of bandwidth, and we've talked about this, the parallel operation, by looking at the parallel implementation of 1 and your loop gain transfer function t of s, and showing how it takes this path here. Now let's go back to talking about what we actually want our loop gain to look like and what our regulator should look like. So right now we've remarked that it's a little bit qualitative whether this condition was met right here. And I've showed you down here how if we have 1 in parallel with 10, we end up having, something around a little bit less than 10% error in our output. So in a lot of applications that won't be good enough. And so what we'd actually like to have happen is we'd like our loop gain to look something like this. So it can, in the high frequency regime, it can follow the path that it's currently on. But in the low frequency regime, we'd like it to keep increasing as our frequency decreases. As far as we're concerned, it'd be great if that just continued off towards infinity for 0 hertz. Because if it's infinity, if you're down here and you've got 1 in parallel with infinity, that is exactly equal to 1. And that's what we really want. So how can we make that happen? Well, we started to paint the picture in our last video, but the idea is that we can accomplish this by having a regulator which has a transfer function that looks like this. Again, we're running out of colors here. I'll use some orange. So if our regulator has a transfer function that takes this path, we can see that if we were to add GR2 to the kernel of our loop gain, we'll end up with that Brown transfer function. So let me draw that Brown transfer function a little bit more clear. The Brown transfer function is taking this path right here. And this is the transfer function that we want. This is our desired loop gain. And we're making that desired loop gain happen by the transfer function that we've sketched in orange, by the regulator transfer function that we've sketched in orange, which is this. So if you add the orange to the blue, you end up getting the brown. And how do you make the orange happen? Well, you can see this as the addition of 2 transfer functions again, like we've been doing up to this point. So we can say that now we're going to do regulator 2, which is our better regulator, as being equal to, first in the high frequency regime, we want it to be equal to 20 decibels. So we'll say it's going to be equal to 10, which is 20 decibels, plus a transfer function that actually takes the path of the brown line, and that transfer function is just 2 pi 10k over s. So we can see that this transfer function is going to be unity at 10 kilohertz, or 0 decibels at 10 kilohertz, which is what we have up here. That's right there. And if we work with this a little bit, we can put it into the form of an inverted 0, which is equal to some gain times 1 plus the form of an inverted 0, where omega z is equal to 2 pi times 1,000, and our gain is equal to 10. And this is the form of a PI regulator. A PI regulator has a transfer function of Kp plus Ki over S. And so in this case, Kp is equal to 10, and Ki is equal to 2 pi times 10 kilohertz. So let's now plot what our phase angle looks like. And we can see from this transfer function that in the low frequency regime, when omega is small, omega z by j omega is going to dominate, so we're going to have negative 90 degrees in the low frequency regime. And in the high frequency regime, we're going to have 0 degrees, because omega z over j omega is going to be a very small value when omega is large. So at omega z divided by j omega equal to 1, which is at 1 kilohertz, we're going to have negative 45 degrees for a phase angle. So that means it's going to look like this. It's going to be negative 90 degrees. It's going to go up to negative 45 at 1 kilohertz, and then be at 0 degrees by 10 kilohertz, and then remain at 0 degrees out into infinity. And we can now plot the phase angle of our loop gain for our new transfer function by adding the orange and the blue lines, because we're multiplying gr2 times tk. So if we do this, we start out at negative 90, and we stay at negative 90 because we're adding the blue and the orange right now, all the way out to infinity. So we stay at negative 90 the entire time. So at this point, we can see that we've satisfied all of our design criteria. With the first criteria, we cross the 0 dB point at negative 20 decibels per decade, so we've met that. We have a gain crossover frequency, which is less than our phase inversion frequency, and we can see that that as omega goes to 0, our loop gain goes to infinity. So we've checked off all three of these boxes. We'll actually have no steady state error at 0 hertz. And this is important not only in the sense of rejecting disturbances, but also to accommodate for nonlinearities and non-idealities within our system. So, for example, if we think that V peak has a value of 10, but it actually has a value of 9.9 volts, when we give an input reference, we're never going to calculate the exact right duty ratio. So it's important to have a large loop gain to compensate for this. So if we have a large loop gain, the regulator will overcome these non-idealities and give us our desired output without any error. Okay, so that concludes this video. To summarize, we've been digging in a little bit deeper on the design approach for regulators and building up our physical intuition for how it behaves within our system.